Right, so the next speaker is Benito Juárez-Aubry, and he will talk about quantum strong cosmic censorship and black hole evaporation. So please, Benito, the floor is yours.
Okay, thank you very much. I'm very happy to have the chance to talk to you all. I have to say I find this initiative very exciting, just to put that up front. I even tried to maybe convince some colleagues in Mexico to have one of our own, institutional circuit and so on. But okay, unfortunately, it didn't work out. But I'm happy to be part of the last day of the miscellaneous kind of talks. Okay, maybe next year I'll try harder to convince them, right? Okay, so I want to talk about a question that has been around since, already for a good 40 plus years, which has to do with black hole evaporation. And I wanted to share my views on this issue. In particular, to give perhaps some mathematically precise, in some sense, arguments as to how we could probably think that information is not lost in a very, very particular way, which I will explain, having to do with mainly a series of arguments that seem to point, in my opinion, in the direction that quite probably at very late times in black hole evaporation, the semiclassical description of the black hole evaporation leads to divergences, which do not allow, in some sense, to say anything beyond a certain Cauchy horizon that appears on the evaporation diagram. And that, in my opinion, this indicates that the original presumption that there's a post-evaporation region where information is lost is not really justified. So I'll make the point throughout my slides, and in doing so, I'll present some kind of generic idea about strong cosmic censorship in a quantum setting. So that'll be kind of the main point of the talk, and then explain this in the context of black holes, which is in some sense the inspiration for this idea. Anyway, so let me give you my outline. Of course, everyone knows black hole evaporation, but I'll touch on the issue very quickly. Then I'll talk about the puzzle itself, the information loss puzzle, and then I'll tell you about my idea on quantum strong cosmic censorship, and then I will argue that this supports unitary evaporation of black holes. Okay, so first of all, we know that black holes radiate. In the 70s, Hawking wrote an incredible paper in which he found that black holes emit radiation. And it goes as follows. In the process of the formation of a black hole, quantum fields start getting stimulated, and there's particle creation. So this is in some sense not incredibly surprising, because black hole formation is not a stationary process. And we already knew from the work of Parker that in non-stationary situation, one has particle creations. Now, what's more interesting is that at late times, once the black hole has formed due to this stellar collapse, the creation of particles has a thermal spectrum. So in particular, in the test field limit, the radiation is thermal. So by this test field limit, I mean quantum field theory of spacetime. The radiation is thermal at the Hawking temperature, which is proportional to the surface gravity of the black hole. So for example, for Schwarzschild, we know very well that this is 1/8 pi, the mass parameter of the black hole. Okay, so this is not super surprising now after, so many years, because an exterior observer in some sense has no access to the details of whatever is going on inside the black hole. And thus a pure state, if you trace out, formally speaking, over the interior degrees of freedom of the black hole, looks thermal. Okay, so note that generically, the Hawking temperature will depend only on the mass, angular momentum, and charge of the black hole. Okay, because these are the parameters that the surface gravity is going to depend on. Okay. Now the second part of the story is that black holes evaporate. There is an energy flux at the black hole horizon that is negative. So that means that there's output of radiation is making the black hole shrink. in some semi-classical sense. Now, if the black hole shrinks, it becomes hotter by this Hawking temperature formula. At least in a quasi-stationary regime, if you think this formula still is reasonable, you expect the black hole to get hotter and hotter, and eventually, people argue evaporation cannot be stopped, and I think there's good reasons to think that's the case. Okay, eventually one ends up with the following diagram, which I will explain. So this is the diagram that Hawking drew in 1975. You initially, can you see my little hand? I suppose you can. So I will assume you can, actually. So you have initially a star collapsing and forming a black hole. So the black hole region is this blue region, okay? And if you have an initial in state, for example, defined on SCRI minus, you have this radiation kicking in and starting to go carrying energy away from the black hole, making it shrink, until eventually the black hole completely shrinks, and you end up with a diagram that looks like that. In the far future, there is no black hole. There is a region that looks kind of flat or almost flat, and is completely full of radiation. So in this diagram, when you initially had a mixed and a pure state on SCRI minus, you will end up with quite general arguments indicate that you will end up with a mixed state on SCRI plus. And of course, this indicates that this whole process is not unitary, because we don't see this non-unitary, we don't see pure going to mixed in unitary evolution. Okay, this is the information loss puzzle. How is it possible to reconcile the idea that we have non-unitary evolution in the evaporation of a black hole, and where does the information that was contained in this pure state, where did it all go? Okay. Now, it's noteworthy pointing out that the previous diagram is not globally hyperbolic. Let me just go back to the diagram to indicate why. If you start out with a Cauchy, well, not Cauchy surface, because this is not globally hyperbolic, but if you start out with what would be a Cauchy surface of some domain of dependence, you can only get up to here, for example, because there at this point there's a Cauchy horizon. Okay, so if I take, for example, SCRI minus and I give initial data here, I know how to evolve a hyperbolic equation up to this point. So this boundary of this red region is a Cauchy horizon. Okay. So information loss is a manifestation of this lack of global hyperbolicity. There is a breakdown of quantum and classical determinism. So breakdown of quantum determinism is what we refer to as information loss. And this point has been emphasized, for example, by people like Andrew, by people like Wald, and I think they are correct in their remark. Okay, however, there is, in the last few years, very strong evidence that Cauchy horizons are not semi-classically stable. That means that quantum effects become, apparently, under quite generic circumstances, quite important in Cauchy horizons. So the point I want to make is that this semi-classical instability is contrary to the standard information loss picture. Okay, so that this instability will not allow you to draw this diagram where there's a post-evaporation region. That's what I want to say. So let me begin by providing a precise statement, which is unfortunate that I have to talk about mathematics and so on now. Okay, so I'll talk about algebras of observables and states in curved spacetime just because the main idea is conveyed in this language, okay? So we can view algebra of observables in spacetime as associated to spacetime regions. This is kind of the moral of the algebraic approach to quantum field theory. So rather than giving you a very complicated mathematical definition, I'll give you an example, which is the Klein-Gordon field, okay? So a Klein-Gordon algebra in a fixed globally hyperbolic spacetime is a unital star algebra, which is generated by some symbols that are smeared fields. So if I give you a test function, which is smooth and of compact support, I can draw these symbols and impose a series of relations on them. So I can ask that there's a linear map from F to the smeared field. So that means that's just a distribution. I can ask for hermeticity. I can impose a field equation weakly. So that means that acting on test functions, this is 0. So you can think of it holding by integration by parts twice. And then I impose commutation relations where this is just the causal propagator. This is just the covariant version of the standard commutation relations. Now there are some additional properties of this of this algebraic construction. If you take a smaller region than the full globally hyperbolic spacetime, then the smaller region, if it's a globally hyperbolic spacetime in its own right with the induced metric, you can define an algebra in that region. And furthermore, that algebra is isomorphic to the subalgebra of the algebra defined in the larger region, restricted to that smaller piece. Okay, and then there are a few other axioms such as time slice axiom and so on. Okay, this is not, I don't want to spend too much time here. Okay, and now what I mean by states is a linear map going from the algebra to a complex number such that it's normalized. Okay, so the identity has to go to 1, and it's positive. Okay, so whenever you take the expectation value of A star A, this has to be non-negative. Okay, a state is in general defined by all endpoint functions, and then by the GNS construction, one can obtain a representation of this algebra in Hilbert space. Okay, for our purposes, all of this blah, 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 the most important one is the 2-point function. Okay, so the 2-point function has an integral kernel that everybody knows and loves, and that comes from this kind of we know very well from our master courses in quantum field theory, which is the Weidmann function. So for example, in Minkowski space, this is exactly what we know from this kind of mode expansion formula. Or there's also a closed form version in terms of Bessel functions. Okay. And a very important property of states is the Hadamard condition. Okay, so that's a condition of the 2-point function. It doesn't care about all the other endpoint functions, it cares about the 2-point function. So it prescribes in some precise way what are the distributional singularities of the 2-point function. So there's a complicated, definition, but morally speaking, think of it this way. The 2-point function is a bidistribution, so it's a distribution of 2 points. And the leading divergence in this Hadamard states goes like a smooth function, which is actually 1 in the coincidence x goes to x prime or x prime goes to x, divided by 1/2 of the square of the geodesic distance between the points x prime and x. And this epsilon is just a regulator. It's just to give a distributional correct description of the Weidmann function. Then there's a subleading divergence, which is logarithmic, and it comes multiplied also by this smooth symmetric coefficient, okay? And then there's another piece that is completely regular. In fact, it's smooth typically, okay? So you can say this in a very precise way, but just get the right message that this goes like 1 over sigma, where sigma is the square of the geodesic distance between these 2 points. So when these 2 points are connected by null rays, of course, this is the distributional singularity. So this is exactly like in Minkowski space, but in curved spacetimes. Okay. So let me get now to this conjecture. I'll give some auxiliary definitions before I state it. So first definition. If you have a spacetime and S is a partial Cauchy surface, so a closed achronal set, such that its domain of dependence is not its causal shadow, then we say that it is a strictly partial Cauchy surface if it cannot be extended to be a Cauchy surface on the conformal completion of this spacetime, or if it admits an extension to a Cauchy surface, we say that this extension, the extension is such that if you remove this partial Cauchy surface from C, the extension, then there is an open set of C contained in the interior of the conformal completion of the spacetime. Okay, it looks complicated, but I'll give an example of why this is important. Then we have another quick definition, which is quite standard. If you have a star algebra A hat, we say it's an algebra extension of a star algebra A if A is a star subalgebra of A hat. And if we have a state on A, then we say that the state omega hat is a state extension of omega if omega hat of A is equal to omega A for all the A's in the subalgebra. Okay, so it's just a natural notion of extension. Okay, so let me get to the conjecture. Let S be a strictly partial Cauchy surface, okay, of the not necessarily global hyperbolic inextendable spacetime MG. And you take its domain of dependence to be ds. So ds with the induced metric can be seen as a globally hyperbolic spacetime in its own right. Okay, so here I'm just saying that this is the induced metric. Okay, you pull back and so on. So let A be an F local. This is just a technical condition. Quantum field theory defined over the whole spacetime, and let B be a quantum field theory, free or perturbatively interacting. I should also say A is free or perturbatively interacting. Quantum field theory over the domain of dependence, okay, which is isomorphic to this subalgebra of the whole larger algebra. Then, if you have a state on the smaller algebra that is defined only on the domain of dependence, that is a pure Hadamard state, then generically there is no extension of this state defined on the domain of dependence of this partial Cauchy surface to a state defined on the larger algebra, so in particular on the closure of this region, that is Hadamard. So what does this mean? I define a pure state in a small region that is the domain of dependence of some strictly partial Cauchy surface, and then when I try to get to the boundary of this region, so which is the Cauchy horizon, then I lose the Hadamard property. Okay, that's what it says here in words. Okay, so a breakdown of the Hadamard condition might, of course, indicate a breakdown of semiclassical gravity. For example, it might indicate that the stress energy tensor doesn't exist, but rather its expectation value. And of course, this is the source of the semiclassical Einstein equations, which are given by equation 4. Now, if the breakdown is sufficiently strong, one might develop, for example, semiclassical curvature singularities on the left-hand side. So I argue this is what happens in black hole evaporation. And so I argue final stage of black hole evaporation is beyond the semiclassical regime of quantum gravity. Now, remarks on the hypothesis. The strictly partial Cauchy hypothesis is important. And there's a good counterexample, which was mentioned to me by Jorma Loco, and since then I've understood that there are other ones as well. So consider Milne's universe, which is the future wedge in Minkowski space. It's possible to construct a pure state in that space-time that can be extended to the whole of Minkowski vacuum. But here, a Cauchy surface of Milne is not a strictly partial Cauchy surface in Minkowski. Rick, how am I doing with time? Am I still good? Sorry? Okay, so I'll speed up, but I'm almost done. So purity, of course, there are plenty of examples with mixed states that can be extended. For example, a thermal state at the Unruh temperature on the right Rindler wedge extends to Minkowski, so that's quite clear. F locality is just a technical point, which I will not dwell into. And finally, genericity. There are finely tuned counterexamples. For example, if you take a conformal blow-up in an otherwise globally hyperbolic spacetime and remove the blow-up point, then you can define conformal states that are Hadamard everywhere in this non-global hyperbolic spacetime. Okay, a number of authors have observed the breakdown of the Hadamard property in Cauchy horizons. So, okay, for example, the Rindler state on the Rindler wedge in flat spacetime, the Unruh and Hartle-Hocking states in Reisner-Nostrom in lower dimensions than in 3+1. Likewise for Reisner-Nostrom de Sitter, and more recently with Kerr. So there are plenty of examples of these blowups. There are more importantly structural results, which I will not read in detail, like K. Ratzkowski-Wald, as you know, for compactly generated Cauchy horizons. And another result by Fuster and Ferch that talks about the blowup in diamonds or double cones or diamonds in Minkowski space, in the interior of Minkowski space. Okay, so what I think semiclassical gravity actually predicts, if this conjecture is true, is a final singularity where the Cauchy horizon would form. But now look, this diagram is completely globally hyperbolic and there's no loss of information. Of course, you might say, oh, you've traded loss of information for something horrific. Now everything becomes singular. Sure, but I think that semiclassical gravity is only as good as predicting this. Okay, there are two pieces of evidence for why I think this is correct. The final evaporation event is a curvature singularity, and if semiclassical gravity is reasonable in some sense, you would expect the singularity to propagate causally, okay, or Allen cones. Also, if you think that the Hocking temperature becomes hotter and hotter, then you expect a breakdown of the Hadamard condition. So this has led me to a stronger conjecture in semiclassical gravity, which I am not stating here, but it's in my preprint. And what I think quantum gravity ought to do is to resolve this final singularity and give us a diagram that looks like this, okay? So perfectly nice with a color that we don't understand at all because it's in the strong quantum gravity regime, but otherwise looking very globally hyperbolic. So thank you. I would very much like if you look at my preprint and give me some feedback. I was expecting to be the last speaker in this event, so I included this big clap for the organizers of this successful initiative. I think we can still clap even if I'm not the last one. Thank you.
Thanks, Benito.